knows a lot about the science stuff. Professor Dave explains.
Throughout this series, we've discussed many details about all the particles that make up the Standard Model. We've also talked about how incredible of a job the model does of explaining the world around us. As we've said, it's arguably the most successful scientific theory ever developed. Although, thanks to modern cosmology, we know that all of the constituents of the Standard Model only make up approximately 5% of our universe. This means that 95% of the universe is beyond the scope of the Standard Model. What is all this stuff filling up spacetime? According to the Lambda CDM model of cosmology, which is the current best theory to explain our universe, 27% of the universe is made up of dark matter, and 68% is made up of dark energy. Together, these make up a part of the physics world known as the dark sector. But what are these dark mysteries that fill 95% of the universe? Dark matter is a theorized type of matter that has been proposed to describe many irregularities and inconsistencies across decades of experiments. It is an umbrella term for any matter that interacts with the Standard Model through forces that are not electromagnetic. In other words, the matter is dark because photons can't interact with or illuminate it the way they do with baryonic matter, with electrons absorbing and emitting photons as electrons move between energy levels. However, the term dark matter does not currently refer to a specific particle. It refers to the large body of evidence that suggests there is much more matter in our universe than we can see. The first main hint at the existence of dark matter was discovered by Vera Rubin in the late 1970s. She showed that the speed of a galaxy's rotation did not decrease as you looked at matter further out from the center of a galaxy, which was contrary to the naive expectations of how gravitationally bound systems work. If the only matter within the galaxy was the matter that we can see, the light matter, then the equations of physics tell us that the rotation curve should follow the dashed line. However, many observations show us that it follows the solid line. This indicates that hiding in the galaxy somewhere is a bunch more mass that we can't see, which we call dark matter. Another famous example of evidence for dark matter is the bullet cluster. This is a famous image of two galaxies that have smashed into each other. On the right, you can see the bullet that has shot through the larger cluster on the left. All of the hot gas shown in red within the galaxies is full of particles that undergo electromagnetic interactions, and therefore have collided and experienced a drag force as the galaxies passed through each other. This slowed the gas down and didn't allow it to travel as far. However, by analyzing the effect of gravity on the light coming from the stars behind these galaxies through a technique called gravitational lensing, physicists can determine where the concentration of mass for each galaxy is. These centers of mass are shown in blue in the image. Clearly, the majority of the mass from the galaxy has passed through the other galaxy without interacting much and has traveled farther. Since dark matter does not interact electromagnetically, the dominant interaction being gravitational, dark matter is the perfect way to explain how much of the mass seems to pass through unaffected. Additionally, it must make up a large portion of the mass of each galaxy. On top of these two examples, there is a tremendous amount of evidence through further gravitational lensing investigations and cosmological analysis of our universe and its origins that is outside the scope of this tutorial. A small portion of the scientific community still believes that all of this could be explained by modifying gravity instead of considering new matter, but the vast majority have been convinced that dark matter is real outside of the Standard Model and should be searched for. Agreeing that dark matter exists is an important first step, but how do experiments actually look for it? The techniques can be grouped into two main categories: direct and indirect detection. Direct detection aims to observe dark matter particles bumping into ordinary Standard Model particles in ultra-quiet, low-background detectors. These are generally placed underground, often in abandoned mines or underneath mountains, to reduce the cosmic rays and other noise sources that could inhibit detection capability. The signal that these experiments are searching for is extremely tiny and hard to find, so experiments push backgrounds as close as possible to zero with shielding, extremely pure materials, pulse shape discrimination to identify exact event sources, and precisely engineered readout channels. On the other hand, indirect detection looks for the products from dark matter annihilation or decay. This could be something like gamma rays, other high-energy photons, antimatter, or neutrinos. Often this is done by looking at places where dark matter is believed to be piled up. For example, the center of the Milky Way or another galaxy, the Sun, or galaxy clusters. Colliders like the LHC can also try to do a third method of detection where they make dark matter inside the collider by smashing standard model particles together in the proper way. Then, since it won't interact with any of the detectors, they reconstruct the event that took place and look for any missing energy or momentum. Around the world today, experimental searches for dark matter are generally looking for one of two types. Over 40 years ago, theoretical physicists realized that if a particle with a large mass, typically of around 10 giga-electron volts to 1 tera-electron volt, interacted via the weak force and was present in the early universe, they could run it through equations that describe the universe's evolution, and it would match the exact amount of dark matter present today. This was known as the WIMP miracle, where WIMP stands for weakly interacting massive particle, and weakly interacting indicates that it interacts via the weak force. One of the experiments looking for these WIMPs is a direct detection experiment called the Cryogenic Dark Matter Search, or CDMS, and the new generation is called Super CDMS. They cool detectors made of germanium and silicon down to temperatures near absolute zero, and look for the recoil from dark matter hitting the nuclei within the detectors. Many other experiments have spent years looking for WIMPs, and so far nothing has been found. Today, after decades of WIMP hunts, sensitivity has crossed key thermal relic targets, which predict the correct dark matter abundance, assuming WIMPs were once in thermal equilibrium for many masses, so the community is broadening the search to non-WIMP candidates. It appears that the tides are turning towards another possibility for the nature of dark matter. Remember how we mentioned something called the strong CP problem? In QCD, there is a theta term that would violate CP and give the neutron an electric dipole moment. However, the upper bound on the neutron EDM from experiments tells us that theta must be less than 10 to the negative 10. This implies that theta is extremely small, or could even be zero, and this makes physicists uncomfortable. Why would nature choose such a microscopically tiny number? To solve this, in 1977, Roberto Peccei and Helen Quinn proposed the idea that theta is not a constant, but rather varies with a dynamical field that takes a minimum value of zero when the Peccei-Quinn symmetry spontaneously breaks. This is similar to the Higgs spontaneous symmetry breaking we talked about. In 1978, Frank Wilczek and Steven Weinberg both independently came up with the idea of a particle called the Axion that would emerge as the Goldstone boson of this symmetry breaking. It was named the Axion after the soap since it cleaned up the strong CP problem. Then, physicists realized that these light axion particles could be an explanation for dark matter as well. After all, they would be long-lived and weakly interacting. There is also a whole group of particles that has now been developed known as axion-like particles, or ALPs, which are similarly possible dark matter candidates, but don't necessarily solve the CP problem like the original QCD axion. Fortunately for researchers, axions have another useful property. They are believed to be able to convert into photons and vice versa. This allows for both direct and indirect detection techniques to be used. Some experiments, such as Haystack, DM radio, Abracadabra, and most famously ADMX, essentially just use a strong magnet to convert axions into photons and then use a radio to listen for the signal. Even more fortunately for researchers, axions might also couple to atomic nuclei via gluons. An example of an experiment examining this is CASPR, which searches for a nuclear magnetic resonance signal induced by a torque on the nuclei coming from the axion field. Indirect detection techniques can also leverage all the axions' potential couplings by looking at supernovae and studying other cosmological phenomena like baryon acoustic oscillations. Okay, all this talk about dark matter is cool, but what about the other 68% of our universe? This portion of the dark sector has a fascinating story. When Albert Einstein was developing his theory of general relativity, he was convinced that the universe was static. To prevent this assumption from causing his equations to indicate that the universe would quickly implode on itself, which it clearly hasn't done yet, he added a term that he called a cosmological constant. This was a term that essentially countered gravity, acting as a gravitational repulsion. compulsion. Since he didn't feel the existence of the term was physically motivated, he called this his biggest blunder. Later, once Edwin Hubble proved the universe was expanding rather than static, this cosmological constant was abandoned. Then, in 1998, Adam Rees, Saul Perlmutter, and Brian Schmidt studied Type 1a supernovae. They knew the exact brightness that these cosmic light sources should shine with, so they could use the brightness measured on Earth to determine how far away the sources were. By doing this, they determined that the universe's expansion was accelerating. How could this be? Dark energy is the term that physicists came up with to describe the mysterious cause of this accelerated expansion. But what exactly is dark energy? Well, some physicists believe it could be related to Einstein's cosmological constant. An accelerated expansion points to some force that is directly countering gravity and pushing everything apart, so maybe it wasn't a blunder after all. Other physicists believe dark energy could be a scalar field called quintessence, while others still believe it could be some new particle. In that case, it could be searched for with particle physics techniques and eventually added into some new and improved version of the Standard Model. Together, dark matter and dark energy make up 95% of our universe. This means that although the Standard Model is a phenomenal theory, it is clearly missing some key components. Along with all of the other exciting tests of the model, searches for answers about the dark sector provide a rich opportunity to discover new physics that the Standard Model cannot yet describe.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.